Okay, just wanted to give you a quick summarization of the lab, part 3 of that lab that we've been doing. So if you remember, we plotted force of gravity versus this weird thing, massive red times massive blue, all over d squared. And the reason we did that, if you remember, is because we looked at the relationship between force of gravity and mass, and we saw that they were directly proportional. And that's why it's on the numerator down here, is because they are directly proportional. Anytime something's directly proportional with each other, you want to put it on the numerator of the equation. And so force of gravity is also inversely proportional to d squared, or you could say that that's directly proportional to 1 over d squared, and that's why d squared is in the numerator here. And so all we did to find this was take the mass of the red object times the mass of the blue object divided by the d squared, and it didn't matter what the d was, didn't matter what the mass of the objects were. It's always going to give us a value that fits along this line. And so we got a line when we plotted that, and we'll talk about the meaning of the line here in just a second, but I do want to talk for a second about the units. When you plug this in, you get kilograms times kilograms, which comes out to be kilograms squared, and then you take meters and you square it, and so therefore it's meters squared on the denominator. So this is a weird unit of kilograms squared over meters squared. Now the value of that slope and the equation for that line I'm about to give you, but basically the equation for the line should be the y value, which is at force, is equal to the slope of this line times massive red times massive blue all over d squared. And that's what I have on the next page right here. It's right there. There is the equation right there. And this is the slope that you should be getting, and this part right here is the units of the slope, and I'll talk about the units first. So the units of the slope, because I've got, to start off with, I had kilograms squared over meters squared on the x-axis. And then to solve for that, to solve for the value, the units of the slope, I took rise over run. Well, the rise unit is newtons, the run unit is kilograms squared over meters squared, and so therefore I would take newtons, put it on the numerator, and then meters squared would be on the denominator. Now, what we have just done here is we have come up with Newton's universal law of gravitation. And you may be thinking, man, this is a weird equation, but it's fundamental in our understanding of gravity as we know it today, because the force of gravity is not just simply a force that holds me on Earth. It's much more than that. Because according to this equation, the requirements for a force of gravity is that you have to have an object with mass, you have to have a second object with mass, and all they have to do is those masses have to have a little bit of have distance between them. So for instance, me, I have mass. You have mass. D, we have a distance between us. Therefore, there is going to be a force of gravitational attraction between us. Even if I were to go on vacation to Timbuktu and you would go on a vacation to Siberia, we would still have a gravitational attraction to us. In fact, you are gravitationally attracted to every single person on this earth. However, there's a problem with that, because this value of the slope is so incredibly small. And so the question you may be asking, based on what I just said, is why don't we draw that on a force diagram? Well, the reason we don't draw it on a force diagram is because, let's just make up a number. If I got 50 kilograms here and 50 kilograms here, so two people with 50 kilogram mass, you multiply those guys together, and let's say they're standing a meter apart. 50 times 50 would be 2,500 newtons. Well, 2,500 newtons would be times 6.67 times 10 to the negative 11. That's going to be like 0.000000000 something in terms of their force of gravity. It's negligible. It's almost nothing. And so therefore, the force of gravity is a very weak force in relation to other types of forces that we've talked about. But this is fundamental in our understanding of universal law of gravitation. Now, the 6.67 times 10 to the negative 11, that's also what we call big G, or what is also known as the gravitational constant. This is 6.67 times 10 to the negative 11, obviously with the same units that I had up here. I just didn't copy them down there. And so the version of the equation can be rewritten as F is equal to big G times m red times m blue all over d squared. Now again, this isn't m red and m blue per se, it's just mass of object 1 times mass of object 2. Anything with two masses would work. Now, one last thing, Newton did not come up with this 6.67 times 10 to the negative 11. He did come up with the relationship between force of gravity and these objects, but he did not come up with the value of the slope of that line. That was something that Henry Cavendish did, which you guys are about to watch a video on.